Here we begin on chapter 1 as usual, but in this time we are advancing to section 2. So last time we talked about 1-1, statistical and critical thinking, the basic idea of statistics. And the basic idea involved wanting to know something about a large population and looking at a smaller sample of that population to get an idea of what's going on for the whole population. And that the big picture for statistics is that you have a population you're interested in and a parameter that you're going to investigate. Again, I'm going to start using the vocabulary that we talked about last time to help everybody get used to it, help your brains accept this vocabulary. So a parameter is a measurement about a bigger population, like all the students at DVC, how tall are they? That's a parameter. And what a statistic is that's where you take a sample from that population and you measure that, the same thing the parameter would have been telling us, but you measure it for your sample, and that gives you a statistic. So I might take a statistic, a measurement of the sample heights of the overall population of students at DVC. And then by looking at the information from the statistic, I can then try to make an inference or understand better what's going on with the overall population. So to look at this more carefully in section 1.2, we're going to look at the types of data. So there's the overall big picture of what we're trying to accomplish, but then we're going to zoom in and just focus on what does data look like? What are the different kinds of data that you can collect? And this is important because understanding the data that you're working with also gives you some ideas about how to analyze it. For example, if I'm collecting average heights of students, I might be able to produce some analysis like what the average height of my sample was. But if I'm collecting eye color of students, there's no such thing as an average of colors because those aren't numbers, right? And so you can't make that analysis for that type of data. All right, so let's move forward in looking at what are going to be different types of data. So the key concept, a major use of statistics is to collect and use sample data to make conclusions about populations. And so the reason that's the key concept for this section is because we're going to be looking at these sample data types. What does the data look like? And then we'll be able to do analysis with it after that. So again, using some of this vocabulary to move forward, a parameter is a numerical measurement describing some characteristic of a population. So in my ongoing example that I'm going to keep using, if I'm talking about the students at DVC as my population, and I'm thinking about how tall they are, then measuring how tall all the students at DVC are for the entire population, that's a parameter. A numerical measurement describing some characteristic of a population. In this case, how tall are the students at DVC is an example of a parameter. So can someone offer up their own example of some made up parameter that they can think of just using your imagination?
Students with green eyes.
Okay, so your population, I believe I heard students with green eyes. Does that sound right?
Yeah.
Okay, so your population is students. And what is the measurement describing some aspect of the population?
The color of the eyes.
Good. Okay, so in the case of what's on the screen here, does that fit the definition of a parameter? No opinion? What do you guys think? Color of eyes, is that an example of a parameter?
It's not numerical, so it's
Yeah.
probably not.
So yeah, illustrating what it says here, it says a numerical measurement. And since color of eyes is not numerical, that would not be a parameter. Now, that is something that can be measured about a population. And so, for example, that would be a different kind of data. And we're going to see soon that the name for that is nominal or even categorical, that there are other ways to describe data that are not numbers. But do notice that in the definition here, it does say a numerical measurement describing some characteristic of a population. And as you can see, as you're trying to learn what these words mean, you kind of have to try them out in your mind. You have to like give them a test drive. You have to try using them and thinking of examples and things like that. Anybody else willing to try to offer up a possible parameter?
Height of students in feet and inches.
You don't get to steal mine. Come on, it's got to be a new one.
What about the weight of students?
Absolutely. Yeah. How much do they weigh? And it doesn't have to be students. So let's say you could go into the DVC bookstore because you're kind of wondering when students are getting books, you know, how much do these things weigh? They got to carry them around campus. You know, how much of a burden is that? You know, is that a real problem for disabled students or something like that? So you could take a parameter or look at the parameter of how much textbooks at DVC weigh. And then you could just go through the bookstore and take each textbook and weigh it, and you could collect that data. Questions, comments, discussions about that? Okay, so far so good. Great, thanks for all of the suggestions. And again, whether you give an example that is not a valid example or is a valid example, it's our process of thinking about this and going through it that's valuable. All of those things are incredibly valuable to everyone's understanding. So now a statistic is a numerical measurement describing some characteristic of a sample. So basically, when you are trying to investigate a parameter, but there's too many things to get the data from everything, then you collect a statistic. You take a sample of all the things that you're considering, and then you look at the numerical measurement from your sample, and then that's called a statistic. All right, moving forward, and it starts to get worse. All right, so we were just noticing that in the parameter and statistic, it did say numerical. And so a name specifically for numerical data is quantitative. Quantitative or numerical data consists of numbers representing counts or measurements. Counts or measurements. And so they do give us an example. Weights of supermodels. Or another example, the ages of respondents. So these types of measurements are numerical and therefore quantitative, and they consist of numbers that represent a count or a measurement. So can anyone offer up an example of a so far unused quantitative data set?
Income of respondents.
That sounds good. Income is definitely a numerical thing, and it's measuring a count of how much money people get paid in some, say, either for a year or for a month or something like that. So income of respondents is a great example. Maybe one more. Yeah, Allison, right? Amount of money. Amount of money might be different from income. There might be other ways that you measure money. Could be the amount of money that people owe. Maybe one more. Okay, I'll give one more. We could be measuring time. So they have here ages of respondents, and that's an example of a measurement of time. How somebody's age is how long they've been alive. But for example, you could be measuring how fast a car on a racetrack does a lap. And so that would be a measurement of time. So that would be a quantitative data measurement. Okay. Now, just to give you an example of how this vocabulary ends up becoming important, You all have a project due at the end of this semester, so you won't think about it probably till the last month of class. But in the description of the project, it states specifically that you need to collect from your sample both quantitative data and qualitative data. And it even describes what kind of quantitative data. And there have been some instances where students did not collect any quantitative data, and therefore they couldn't do any of the analysis with the data they collected because they had the wrong kind of data. So early on, as we're thinking about these things, you want to sort of put yourself in an active position mentally about imagining using these words and these definitions to actually do things. And we begin by trying to understand the words well enough to classify examples so that you have these words as active vocabulary. Okay. So then kind of the opposite or the alternative to quantitative data, which means that it's involves numbers that measure some counts or something, is categorical data. And it says in parentheses, or qualitative or attribute data. So the two words that you can pair up as sort of contrapositive is, we just looked at quantitative data where the root word is quantity, like how much. And then here we have qualitative data where the root word is quality, like not a measurement, but sort of the quality of something. But categorical is nice too, because you can imagine that the answers of the data are in categories. And so a perfect example we've already discussed so far is eye color. Eye color, the kinds of answers you get will be in categories like green, blue. Those are different categories of eye color. Or that's a qualitative measurement of somebody's eyes about what color it is, or it's an attribute. So it consists of names or labels that are not numbers that represent counts or measurements. So not numbers that represent counts or measurements, but are just names or labels. So clearly, eye color is not a number that represents counts or measurements, but specifically it's saying not numbers that represent counts or measurements because you could have numbers as categorical data if the numbers did not represent a count or measurement. So let me give you an example of that. When you have players on a team, often they will have a number, maybe a jersey number or a player number. Like, the player comes out on the football field, number 25, and so that number doesn't measure anything or doesn't count anything. It's really just a label. And so that is an example of a categorical data value or a categorical type of data, numbers of players' jerseys. Even though they're numbers, it's not numerical data. It's not quantitative data. Does that make sense? Because the number's not measuring anything, it's really just acting as a label. So that's why when it says not numbers, it specifies not numbers that represent counts or measurements. So that's pretty subtle. So let me put a challenge to you guys. Can someone think of another example of a data where they're numbers, but they're sort of categorical numbers. It's not a quantitative measurement, even though they're numbers.
How about when you go to the DMV and you take a number for your turn, that would maybe represent, it doesn't mean anything, but that's just a number assigned to your person, your label. Would that count?
That's a good question. It depends how they use the numbering system. So certainly it sounds like it would be, but I do think it tells you sort of counting where you are in line. So I think there's a count represented there. But when you, for example, become player 25 on a team, you're not 25th of anything. That number was available. And sometimes players even ask for a particular number if it's not used already by another player because they like that number. Does that make sense? Whereas I think a DMV lineup, you can literally say, yeah, I'm 25th in line. So that's counting your place in line.
Gotcha.
So if they were giving out numbers, like now they give out numbers with letters. Oh, I lost my share there. Let me try to replicate that. If they give up numbers with letters, then that's sometimes hard to see what their ordering system is. But I think in general that usually they're counting something there along the way. That's my belief for that. So let's see if I can get back to the screen. So that's a perfect try where the world is a messy place. So there might be some examples that are kind of, you have to think about it to try to figure it out. And those are the best ones to use because that's how you really deepen your understanding. That's how you deepen your understanding of what the concept is and what the words are trying to get at. So that's a great example. I believe that's probably quantitative data in the way that they use it. But I bet you could quickly find something along that line that is a great example. Anybody else want to try?
What about like your license plate number on your vehicle?
Yeah, and I think that's a better example, even though, of course, it's kind of thrown off by the fact that they stick letters in there. So that's kind of giving you a big key. But something that's purely just a number. So that's the perfect example that is when you inventory things. Then very often you get a numerical label that really isn't counting anything. It can be if it literally starts from zero. So yeah, Andrea points out student ID numbers. That's a very good example because they are not continually counting students when they do that. They will reuse old ID numbers from the past. They're cycling back through. So it lost any ability to be a count. It's really just a label. Your student ID number doesn't really count where you are in any position for anything. It's really just a label at that point. Now, of course, if we don't have numbers, then we very quickly and obviously have categorical data. So then eye colors make sense. Let's look at the examples they have here. Gender, male or female. So that's something that can be observed. And obviously that's a categorical. Which category of gender do you fall into? Shirt numbers on professional athletes. That's the one we've kind of already been discussing, which is really just a substitute for names. Number 42, so that they don't, if you can't see exactly who that is, you can look at the shirt number and look them up. Student ID number such, then I can look up that student, even though several students may have a similar name, et cetera, et cetera. All right, so hopefully that discussion helps understand the difference between quantitative data, which is based on quantity, which is numerical and counts something or measures quantity of something, or qualitative or categorical data, which even if it's a number, it's really just buckets of different types of things, different groups or different labels of things. And again, if anybody has a question, feel free to unmute yourself and shout it out or type it into the chat and we'll try to address it. Yes, question.
I have a quick question about the previous slide.
Yeah.
So the bottom example is about numbers, so I get that, but how would you take track of statistics when it's male or female? Like, would you assign a number to male or female, or I'm confused about that.
Yeah, so I don't think they're trying to say that these two examples are ways to keep track of people. So we're just looking at something that is observed and whether the type of observation you're making, whether it's categorical observation, meaning the results that you get can be put into categories, or whether it's a numerical observation, meaning that it's telling you something that was measured about the object. So for example, I can collect different kinds of data about people. So I, for example, can collect whether the gender of the person is male or female. And so that may then I can then get an idea, for example, if I'm talking about students at DVC, what portion of the students at DVC are male versus female? Or what portion of people who play a particular professional sport are male or female? And so that's a type of data that I could collect, and it's an example of categorical data. So I'm not thinking they're saying that that type of data could be used to identify individuals, but you could look at individuals and then the type of analysis you could do is something like, well, how many of the group are male and how many of the group are female? Whereas the example of numbers assigned to individuals, that's a kind of data, but there's nothing about the numbers that is meaningful for the number that's being used. It's really just a label, kind of like their name. So you could collect the data of what numbers have been assigned to athletes on a team, but not to count anything. It would really just be so that you could then look for maybe what numbers haven't been used yet, so that new players could be then given those new numbers instead of one that's already been used, to avoid repetition or something. So I'm not sure if that's exactly what you're asking. There's my first attempt. If I've left you confused, can you ask a follow-up question, or are you satisfied by that, or how's it going?
I think I'm good. Thanks.
Okay. Yeah, so it's the natural tendency for us as we look at these examples is to not just think of the data, but what's the purpose of the data? And we're actually not there yet in our discussion. We're just talking about different kinds of data and how to identify what kind of data you're working with. And then we will be able to use that to talk about what to do with that data, which we'll begin to do in chapter 2. Great question, great discussions, thank you. All right, so working with quantitative data. So quantitative data, again, is the numerical data where you're counting something or measuring something. And so that is what we work with a lot of the time in statistics. And so we're going to now think about ways to describe that kind of data in even more detail. So assuming we're already talking about quantitative data, some numerical measurement of something, it can be further described by distinguishing between two types of quantitative data, namely whether the data is discrete numerical data or whether it is continuous numerical data. And so these distinguish, we need a definition for that. So discrete data result when the data values are quantitative, numerical, measuring something, and the number of values is finite or countable. And so their example is number of tosses of a coin before getting tails. And as we go through examples, it's probably, since these are two different types, it's best for us to immediately look at continuous, and then we can use examples and compare and contrast. So discrete data means finite or countable numerical values. Then the continuous data, on the other hand, is numerical data when you have infinitely many possible values of numerical answers. The collection of values is not countable. So the example they gave for this is lengths of distances from 0 to 12 centimeters. So the previous example for discrete is number of tosses of a coin before getting tails. And the example for continuous is lengths of distances from 0 to 12 centimeters. So we have to wrap our minds around the idea of what do they mean then by countable versus infinite? So why is this a countable thing? Because you're not going to be able to flip a coin forever. At some point, even if you commit to doing it for the rest of your life, you'll die and the coin will no longer be tossed. And then we will see how many tosses were made. And of course, you might get tails hopefully long before then. But even theoretically, you couldn't get heads forever because at some point you can't flip it anymore. And of course, the reality is that it's very unlikely that you will be able to flip it for very long before getting tails. So the number of coin tosses you will get before getting tails would be answers like 0, 1, 2, 3, 4, maybe in some super extreme examples up into the 10s or 20s or 100s, or in a very, very unlikely scenario beyond that. But it's some number that you could kind of count, count out. And so this is a finite possible number of results. So this is discrete because there's only a certain number of answers that you could possibly get that is finite. Questions, comments, discussions about that? So let me give you another example to add to this one. Then we'll go over to continuous, look at a couple more examples of that, and then try to think of things and determine whether they're discrete or continuous. So another example of discrete data would be How many students came to class today? Looks like maybe 20, 21, something like that. So, well, that's going to be a number where there's only possibilities from like, 0 to 30 is basically the limit. And so there's really only about 30 possibilities. And that's definitely finite. So that's an example of a discrete data value. And maybe every day I would make a note of how many students came to class. So then I would have this data set of students that attended every day, and it would be some numbers, but that would be an example of discrete data because the data that I'm collecting has only a finite possible number of results. Even if they repeat, there's only a finite number of different kinds of answers I could get. Questions, comments, discussions about that? All right, so in contrast to that, continuous is where there's infinitely many possibilities. So it says the lengths of distances from 0 to 12. Well, you might think, well, there's only like 12 possibilities there, but that means you're automatically restricting your kind of distance to being a whole number value. But nothing about a distance needs to be restricted to being a whole number value. You could have 5.738924397 centimeters. And if I change any one of those decimal values even a little bit, I get a different number. And there may be limits on how accurately you can measure, but there is no limit on when you're in terms of how the length of a distance from one thing might be from the other. There are infinitely many possible measured distances between 0 and 12. They're only limited by your accuracy, not limited by the nature of the data that you're collecting itself. So this is an example of an infinite type of data, meaning numerical data where there's infinitely many possible results. Whereas the number of students coming to class, I'm never going to have 5.5 students attend class. People, the definition of a student coming to class, you have to have a whole number answer, and that's why we have a limit of like 30 possibilities. So if you're counting numbers of people, there's going to be a finite number of possible results whether you can get. But if you're measuring a distance over some range of values, there's infinitely many possible distances that you could get within that range. Another example of a continuous type would be if we were to measure something else about people, for example, weight or age. There's still possibly some range of limits in values, like you're never going to have somebody over 150 years old, but you could measure their age all the way down to the second, all the way down to the millisecond, et cetera. So because theoretically, the time that someone has been alive has infinitely many possible answers in the range of how accurate that is, that's an example of continuous data. Things that are measured that are quantities that don't have to be like specific chunk values where there's a continuum of answers are continuous values. Weight, time, things like that. Questions, comments, discussion?
So for example, if you were to measure how long someone run, which kind of data will be?
So you're measuring a period of time, and there's no reason, if measured very accurately, to expect that you have to get some kind of a whole number answer. Even if you end up rounding off your answers, the actual measure of time that they ran could be all the way down to the millisecond or the billionth of a second or a trillionth of a second. The idea of measuring an amount of time that something happened is a continuous kind of a data measurement. Does that make sense?
Yeah.
I have a question kind of relating to that. So since speed is in a way like a measurement of time, would that be considered continuous as well?
It would be. It's a measurement of two things compared together, distance versus time, like miles per hour. But both of those are continuous measurements, and making a fraction out of them is not going to change that.
Okay.
Absolutely. So you can already see we went from sort of very clearly understandable to getting hard to understand. Yes, question.
Okay, yeah, sorry. So in the book, they had an example of two different thermometers. One was a digital and one was, I don't know, the regular thermometer. Like
Analog.
yeah, analog. So what is, I didn't really get the difference, like why one was discrete and one was continuous.
Because when you create a digital measuring thing, it can only show you digits.
Okay.
And so it has no way of giving you data of anything like 5.5 degrees,
Okay.
because it goes from the 5 to the 6. Does that make sense?
Yeah.
But if you have a thermometer that's on a scale, you could say, oh, look, the level of the mercury is right between a 5 and a 6, about halfway. I'm going to say it's about 5.5.
Okay.
And it could be a little bit over 5, so I think it's about 5.1. And if that scale is stretched out so I can see very, very clearly smaller amounts, I might even say, I think that's about 5.13298.
Okay. Got it.
Does that make sense?
Yes. Thank you.
That's a very good example. It's hard to, because you're literally measuring the same thing, but a lot of times the way you measurement will change the kind of data you get. Because remember, the data are the observations. They're what you see. And so the way you allow yourself to see something will determine what kind of observations you'll get. Hang in there. I know that all of a sudden got more challenging than often is comfortable. That's natural. That's okay. Anybody else willing to, how about this? Can someone think of an example and describe why they believe it's either continuous or discrete? Notice the jump from understanding a given example to coming up with an example yourself. Because then the idea is not something that you're reading and trying to understand what's said, but you're trying to make it functional in your brain, that your brain can apply the idea. And that's much harder. That's why I ask students to give it a try. And you don't have to share it. Even if you just don't want to put yourself out there in front of the class, that's absolutely fine, even though I welcome you all to do so. And there's no wrong answers, even though I may say you defined it wrong. It helps everybody and you learn from it. And that's why it's good to participate. But notice the difference in difficulty in sort of trying to apply the ideas yourself. And that's really what I'm going to try to highlight for students as we're going along here, to focus on growing your understanding. And it's not about memorization. It's not about, okay, I'm going to write that in my notes, and then if it comes up, I'm going to look in my notes and try to answer the question. You really want this to be as best you can to be functional working knowledge. And that does take a lot more work and is more challenging, as we can see now. All right, let's move on. And you can always ask later. So now it's just going to get worse. Because if that wasn't difficult enough to think about the difference between discrete and continuous data, and you do have a requirement for continuous data in your project as well, there's another way of classifying data to use 4 levels of measurement: nominal, ordinal, interval, and ratio. Because this not only focuses on differences in different types of numerical data, but it also brings in some of the qualitative data or categorical data we were talking about before as well. And I recognize that just by my using these words in sentences, your brain may start to reject that. There's a natural tendency when there's new words that you don't know very well, that you're not comfortable with, if 1 or 2 of them get used together in a sentence, your brain kind of just checks out or just pauses and say, wait, I don't know what that person just said. And if you get too far in a math class and a lot of the vocabulary isn't really learned by your brain yet, very quickly the math discussions can start to sound like a foreign language. It can sound like, and maybe some of you guys have experienced this. Maybe you missed a couple days in a math class or something somewhere in your past, and then you came in and all of a sudden it sounded like the guy was speaking Chinese or something. It's like, I don't know what this guy's talking about. And it's just because there was enough of a pileup of vocabulary words that your brain aren't used to that you just couldn't follow the sentences anymore. And that's normal. That's natural. It's uncomfortable and it can make people nervous. But I strongly recommend, if you're feeling that, and at any time, if any point in this class, if I say something and you're like, what did you just say? go ahead and ask me to repeat that or to say it again or to slow down and explain it, because I'm expecting that sometimes words won't hit people well in a math class, and I'd rather I get a chance to elaborate and explain that better than just march on and lose students as I go. But I don't know when that happens, so I would implore you all to feel free to speak out and let me know if I should say something again or repeat it or explain it better, and I'm always happy and willing to do that. Or I could give another example if the one that I gave wasn't clear. You know, we're still working with this together, but I want to make your time here in these sessions valuable to you. And if I'm rambling on and you don't know what I'm saying, then it's going to lose value for you. And I would prefer to have a chance to save that and get you back involved in understanding what we're talking about if I've lost you. So please help me do that if you can. All right, having said that, let's dive into levels of measurement, because this is, I believe this is the hardest concepts introduced in the section. And I do see students struggle with this the most usually. So let's take a stab at it. So there's those four, and the first of the four is nominal level. Nominal level of measurement characterized by data that consists of names, labels, or categories only. So categorical data is the word we used before, or qualitative data. So nominal is another way to say that. However, specifically, it's that kind of data that cannot be arranged in some order as low to high. So their example, survey responses of yes, no, and undecided. Another example that we looked at from before would be gender, male or female. So this is nominal level, and the word nominal, the root there is name. Think of it that way, like name level data, meaning you're just naming something. Yes, no, undecided. So with our discussion from before, where I brought in to discern, one example of qualitative data was numbers on jerseys. So that is an example of categorical or quantitative data, but that's not nominal. That's not nominal because you can arrange them from low to high. You can sort the jersey numbers, maybe to make it easier to look up a player's name based on their jersey number. You can list them from low to high. Even though that number doesn't measure an amount of something, it is a type of label that can be ordered. Therefore, it is not nominal, because nominal, it says it cannot be arranged in some order, meaning an order that's natural. Obviously, you could always put anything in a particular order if you wanted to, but by the nature of the type of data, that's not a natural thing. So already very confusing, I'm sure. So I mentioned that an additional example is of nominal data is gender. Can someone think of something else that would be an example of a nominal level of measurement for data?
Maybe like your, I guess it's astrological sign, like Cancer, or like, you know, something like that.
Fantastic. That's exactly right. So that's categorical data. You have these categories, and based on basically which sign you're born under. But yeah, there's no ordering to that that's natural. There's no one that's larger or smaller than the other. And note the fact that you cannot be arranged in some order is that you will never have numerical data as nominal, because you can always order numbers from smaller to bigger. So that's where the jersey thing can be a clear distinction. Anybody else want to give a shot at thinking of a nominal level of data measurement?
What about like race or ethnicity?
Perfect. So anytime you think of something that creates categories or buckets that you drop people into that's not numerically organized, you're basically there. So those are all great examples. Absolutely. All right, so let's see what the next level is. Now, these levels also are arranged this way because they help us begin to think about how to organize the data, how we could do analysis, things like that. So ordinal level, and the key root of the word there is order. So we just had nominal, you can't order it, and next up is ordinal. So maybe they add ordering. So it says involves data that can be arranged in some order, but differences obtained by subtraction between data values either cannot be determined or are meaningless. Now, they do give an example here, grades, A, B, C, D, or F. So definitely the way grades have been used for class, order matters. And these have an ordering that's been very well established. And so if you have a bunch of grades, they can be ordered. But this is also a great example because it's not numerical data. So an alternate example that I would give to add to this would be the jerseys that we were talking about before. So there you have a case of numbers on jerseys, and you can order those. You could make a list of players by their jersey number from lowest to highest. So the key is, how is that different from other numerical data? So the way we talked about it before was whether you're really measuring something or just assigning the label. So when you put a jersey number on somebody, you're clearly not measuring anything. So that's a great example. And that's what they're trying to get at when they say that the differences between data values can't be determined or are meaningless. So in this case, if you have labels that can be ordered like letter grades, well, then the differences are meaningless because you can't subtract an A from a B. Subtraction is a process used on numbers, but they're specifically pointing that out because it can get more confusing when you have numerical data that are actual numbers. Whether those numbers have a meaning where subtraction would make sense is their way to try to say whether something is measured by those. Like the fact that one player has a jersey number that's 10 higher than the other player is absolutely meaningless. It doesn't mean that that player is 10 more anything. So that's why the differences don't make any sense. Can someone try to think of an example of data that is ordinal, an ordinal level of data?
The layers of the Earth?
Layers of the Earth, they can be ordered. And when you say layers, I think you're talking about names for different types of layers, right? Not
Yeah.
like depth layers.
Yeah, I mean like the inner core, the mantle, that kind of shit.
Perfect.
Stuff.
There's a natural ordering, but the differences don't make sense because you can't subtract the words. If you talked about the layers of the Earth by the depth, then all of a sudden that would go beyond ordinal because then differences would make sense. So this is 10 feet deeper than that, and I just subtracted. But when you're talking about names of certain different levels, that's a perfect example. So I see city of birth. So city of birth, what do you guys think of that?
I think that was written for nominal.
I'm sorry, I was going to say that.
Yeah.
So city of birth is perfect for nominal, but it doesn't really have an ordering. Now, the key is anytime you attach a name to something, you could sort of do them alphabetical. So we want to stay away from thinking that being able to alphabetize things is a way of ordering. We want that the thing that's being measured can be ordered in some way, from best to worst or lowest to highest. Not that the labels themselves can be ordered, because you could always order any symbols in some symbol system. So for example, grades, there is a sense of worst to best or vice versa. And it just happens to match with an alphabetical ordering. But nonetheless, the grades themselves have an ordering on what is being measured, which is how well you did. And that's what you're really ordering by. Too much math. All right, we've only got about 9 minutes left. So let's get to the last couple levels, at least to have them out there. And then we might be running out of time. So that's ordinal. And so the third out of 4 is interval level. So this involves data that can be arranged in order, and the differences between data values can be found. So as soon as they say differences can be found, then you really need to have numbers, because you find a difference by doing subtraction. And they're meaningful, unlike the differences in the numbers of jerseys. However, there's no natural zero starting point at which none of the quantity is present. So we really have to understand that probably via examples. Now let's look at their example, years. So 1000, 2000, 1776, 1492. So certainly these can be arranged in order, they're numerical. And the differences make a difference because the difference is the amount of time that passed from one year to the other. So that certainly can be found and is meaningful. So why is there no natural zero starting point? Well, because if you go to the year 0, it doesn't mean that there's no years there. Because you can then go to the year -1 BC, -2, -3, right? So that particular year doesn't mean that there's a lack of something. It's just the label that identifies where we started counting, and you can go to the left of that label, to the right of that label. So the best way to understand that is to compare that to where you do have a natural zero. So let's quickly move to that, and then we'll think of other examples of both. So that then gets us to ratio level. Ratio can be arranged in order. Differences can be found and are meaningful. Those were the same for interval. And there is a natural zero starting point where 0 indicates that none of a quantity is present. Differences and ratios are both meaningful. So the example is class times of 50 minutes and 100 minutes. So this becomes something where we can focus on the 0 value. What does that mean? That means at 0 time, the class has not moved forward yet. There's a lack of class time. There's an absence of class time. The 0 is saying that something is absent. Any time of class having occurred is absent. And so for that reason, this is ratio level measurement. One of the ways in which this can be more clear is a lot of times the 0 is very meaningful, meaning there's nothing there, if you can't go into negative numbers in the thing you're measuring. If you can't have less than nothing. If the thing that's being measured, when it gets down to nothing, then that's it. You can't go below that. So another example for interval level measurement would be like temperature Fahrenheit. So differences make sense, but the 0 of 0 degrees doesn't mean that there's an absence of something, where there's a quantity that is not present. 0 is just the point you reach on the scale, and then you can immediately go down below that, -1, -2, -3. So temperature in Fahrenheit or Celsius is an example of interval level measurement. Whereas when you are measuring an amount of something, like how much something weighs, how much time has passed something has been in existence, like how old somebody is, how long a class time has begun and has been running, those all have a point where when you get down to 0, the thing you're measuring is gone, and you can't go below that. The lowest is that you just have none of it. And so those are all examples of ratio level measurements. Questions, comments, discussions about that, or examples to try to classify in any one of these 4 levels that anyone wants to provide? All right, how about this? I will give you an example, think of it like a homework problem or something, and just see if you can get the beginning space of classifying it yourself. The ultimate position to be is for you to produce examples and classify them correctly, because then you're really applying these ideas in their biggest way possible. But a transitionary point to go through is to just start by being given examples and then just trying to think which definition applies. All right, so here's an example. Birth weights. We'll say in ounces. So that's a type of measurement. What type of data would that be? Would that be nominal, ordinal, interval, or ratio?
That would be integral, right? Because you're never going to have a baby that weighs 0 ounces.
So does that mean that the zero measurement is a natural starting point or not a natural starting point?
I guess you would still start from 0 though if you're measuring weight, right?
It means that there was an absence of weight and you can't really go below that. So that's where you start.
Okay.
And that makes it ratio. So you are perfectly correct to immediately skip over the first couple of them. And the hardest, I think, in all of these definitions will be delineating between interval and ratio. So that's the perfect thing to try to do. Questions, comments, discussions about that example? How about color of the peanut M&M that somebody eats?
Nominal.
Nominal. And could you justify that?
They can't be arranged in order from like low to high.
I think my son, who's mildly autistic, would disagree with that. He definitely has an ordering in his mind of which colors are better than which to eat in his peanut M&Ms. But in general, there isn't a natural ordering. That's exactly right. Okay, so real quick, we have just a minute left. So what I want to do is stop this at this point.